Okay, so yesterday we were starting the radial solutions in Rn minus 0. And n is now larger or equal than 2 because n equal 1 has been studied yesterday. Okay? We found an ODE, which I think it was, please tell me if I'm using the same notation as yesterday. Did I use this V? Was V second price?
B rho. Rho.
Rho. It was called rho. Thank you. So this was the notation of this. Rho is positive. So we can put, say, W equal V prime, which gives us V prime plus n minus 1 V over rho equal to 0, which means that if, assuming that this is never 0, okay, we write as V prime divided by V equal 1 minus n over rho. Okay. So this is the V over V rho of V. Okay, and this is d over d rho, say log rho to 1 minus n. Okay. Please check the computations. So we find d over d rho log w divided by equal 0. Okay. Which means that that function is constant, that is, what it is inside must be constant. So, W rho divided by rho minus 1, say some constant. Right? Some constant. Okay. And this gives us we call in this definition, gives us the following solution, which has two cases. So there is some constant that I will fix soon. I think it's this. Now I will check. And then there is some other constant here, 1 over rho to the n minus 2, and then there is here some constant which is, I will specify. So first let me check the constant, then I will tell you what are the meaning of the symbols. So I have to check the constants. 1 over 2 pi. There is some missing n here. Okay. N omega n. Okay. Now I'll tell you what are the meaning of the symbols. Okay. So at the end, our solution u of x, that sometimes I will use also the following notation, maybe g 0 Rn, or also g of x, doesn't matter the notation, so this maybe for the moment is not so important. So the solution, we have solutions which are 1 over 2 pi log of 1 over x in 2 dimensions, and some constant, which is n omega n minus 2, 1 over x to the n minus 2, n larger or equal than 3. Okay, so first of all, so these are radial solutions to our problem. So this is harmonic inner n minus 0 for any n larger or equal than 3, and this is harmonic inner 2 minus 0 when n is equal to 2. Now let's see for the moment the so this is maybe the most the case we will study more. Notice some remarks. What is omega n? So is by definition the Lebesgue measure of the ball, n-dimensional ball of radius 1, okay, centered at 0. So, where B1 is the unit ball centered at 0. So it is this one. Okay, so when n is equal to 3, for instance, when n is equal to 3, this is equal to the volume of the ball 4 pi divided by 3. Okay, for instance, and so on. Now this has a meaning, I think. So let's see which is the meaning of this product. So when I want to compute the Lebesgue measure of the unit ball, what could I do? Well, there is a theorem that says that this is actually, well, how could we compute this? Yes, there are various ways. So let's see how we can compute this. So I have to recall for you, because what I claim is that this is actually, this product here is the n-1 dimensional surface of the boundary of the ball. Okay, that I denoted by this. So this is, so let me denote by this the n-1 dimensional measure. It is called the Hausdorff measure. Doesn't matter the name. The name is not important. This is in 3 dimensions is the 2-dimensional area surface of the boundary of the ball, 4 pi. Okay? It is called the n-1 dimensional Hausdorff measure. If you have never seen it, doesn't matter, but n-1 dimensional Hausdorff measure in a REN is the, maybe you have seen this symbol, no? D sigma?
Yes.
Yeah. Okay, it is the D sigma.
I just have a question. Why we have a symbol constant A? Why we fix it to be this in omega?
Yes. You're right. We could fix any other constant, but we normalize constant for the same reason we did yesterday. You remember we normalized constant yesterday so that when n equal 1, that constant was such that minus u second was equal to delta at the origin. And the constant was such that in one dimension it was 1/2. And with that 1/2 we exactly have this. Now the idea is that for those choice of constants we will have the analog of this. So we will have, those constants are fixed in such a way that minus Laplacian of u is equal to delta 0 in the sense of distributions. Like exactly the same reason than yesterday. Exactly the same. Of course it is more complicated now to prove. So the origin, thank you for the question. So the origin of the choice of this constant is because we want to normalize it. So I claim that we have this relation between. So let's check n equal 3. Just it is not a check. It's just okay. N equal 3. Is it true that 3 omega 3 is sigma 2? Yes. At least this is true. Because this is 4 pi over 3 and this is 4 pi. Okay. In 2 dimensions true, you can check it is true also in any dimension. How do we check this? Okay, there is a theorem here that says that this is
Stokes?
No, it's not Stokes. It's a sort of Fubini-Tonelli type argument. It's a section argument. So it says that, okay, so first of all, first observation, so if omega n is the volume of the ball of radius 1, which is the volume of the ball of radius rho in terms of omega n.
Power times the volume.
Yes, so this is the first remark, okay? Important remark, just by scaling. Second remark is which is this in terms of sigma n minus 1. Suppose that I shrink or I mean expand the ball, and I want to in the ball
n minus 1. N minus 1.
And rho, there is not rho.
Rho n minus 1.
Yes, rho to the n minus 1 multiplied. Exactly, sigma n minus 1. Okay. So we have this just a scaling argument. Okay. Now there is a sort of section theorem that says that if you want to compute the volume of this ball, you can compute the area of all these concentric balls and integrate from 0 to 1, and you get the result. Okay, so this is a theorem that I give. Okay, let's see what happens. So what I claim is that now this is the area.
It's like integrating the density of the function.
Is a sort of section argument like Fubini-Tonelli. You slice the volume with several mutually disjoint slicing, and you integrate all the areas of the slice, n minus 1 dimension of the slice. So this, what I'm saying is that this is equal to, say, bs ds. This is a theorem. You have to take it, or maybe the, okay, let's see, first of all, the result, what results about, so this is equal to omega n, okay. On the other hand, this is what? It is sigma n minus 1, integral from 0 to 1 of what?
Rho.
not rho, but
That's
S as n minus 1 ds. Okay. So this is equal to what? Is equal to sigma n minus 1, and then we want 1 over n, s to the n evaluated so which is exactly a sigma n over n. So we can expect, you see, the formula that omega n is that divided by n, so we expect exactly what I was saying, this general relation between area and volumes in any dimension. Okay? So if you don't accept this proof, because you don't want to use this this section type formula, I can convince you in another way, maybe. Let's see. So in this case, I need to recall you the most important theorem, I would say, at least in this course, but maybe in general, which is the Divergence Theorem, or also called the Gauss-Green Theorem. So let's see. Let me state it in. There are several versions of this theorem, but let us state it. Theorem, Divergence Theorem. So we have some omega, which is supposed to be, say, bounded, open, bounded, and say of class C1. And this is even too much more than the necessary. For instance, boundary of omega Lipschitz would be okay. But let's take it to be C1. Then we take a vector field. Oh, so this is contained in Rn. Then we take a vector field.
Sorry, what do you mean by a domain Rn being of class C1?
No, why you say domain? This is open and bounded.
Okay.
C1. C1 means that locally, boundary of omega around one point of the boundary, so locally around one point, this can be written as a graph of a C1 function of n minus 1 coordinates. Okay. Variables, sorry. n minus 1 variables. And so in a ball, say, around one point, say, on the omega, there is a small ball, small or large, some ball, br x bar, such that this object is the graph with respect to a suitable orthogonal coordinate system, is just a graph, say, of y as some function f of y, where y is in some open set of R minus 1. Y is contained in R minus 1 open. F is of class C1 of the open set U. And say omega is, say, the subgraph. So omega intersection the ball. X bar, say, is the set where is the subgraph. So this is a graph, so y t such t is, say, is less than f of y. And y is mu. Okay. So it means simply that, say, in some coordinate system here, you have a ball, and then this part is graph. Okay. And this part is graph, say. This is graph, this is U, say. And then we have the map identity F. Okay. So this is the graph of F. And this part here is the subgraph of F. Okay. This means that you are of class C1. Okay, so next, what are the data of the statement? So we have a vector field, say it is C1 also, and maybe I need to talk about the trace of eta on the boundary. So let's suppose also that it is C0 omega bar Rn. Okay. Essentially, so the theorem says that, so let's say C1 of omega bar, okay, just to be, okay. Let's do this. C1 of omega bar, so the divergence of eta dx is equal to, so this transform, as you probably know, a volume integral into a surface integral, where this is the outward, this is the unit normal to boundary of omega pointing outward toward Rn minus omega. So it points outside. If it points inside, then you will see minus in the books. If it points outside, there is plus. Okay? So you see, this is the divergence of a vector field. It's okay because eta is C1. As I said, the hypothesis on eta and on omega could be weakened a lot, but just to write something. Okay, this is the trace of eta on the boundary of omega. Since eta is continuous up to the boundary, this is meaningful. This color product is meaningful. Everything is bounded. Here, this is bounded. And this is the theorem. Okay, so keep in mind this theorem because it's really the basic of harmonic of this course. It's maybe okay. Fine. So why I said this given from granted. I don't prove it. I don't prove this theorem. Yes, I want to try to see if I can use this theorem to prove in another way this, let's see, let's consider omega equal the ball, B1, and consider the vector omega is of course open bounded boundary of class is analytic, so and consider eta the identity divided by n, okay, for any x in Rn, in particular for any x in the ball. So which is the divergence? This is a vector field which has a special feature. The divergence is equal to 1. So it's constant divergence vector field. Is this clear? The divergence is by definition the derivative with respect to x1 of the first component, which is x1 over n, plus the derivative with respect to x2 of the second component, which is x2 over n. So 1 over n plus 1 over n plus n times. So this is 1. So this means that we can do easily this. If I take omega the ball and eta this special vector field, what is the result of this integral?
Ln of p.
Which is denoted by
With W.
omega n.
Omega.
Fine. And now we have the scalar product of our vector field against the normal to the boundary of the ball, and the normal is pointing outside. Okay? So this is what? Is the 1 over n, because our eta has 1 over n here, and then we have the boundary of the ball, and then we have the scalar product of x times nu exterior, which is the expression of nu exterior on the boundary of the ball.
Radial.
It's surely radial, and therefore nu omega of x, nu b1 of x is equal to what? On the boundary?
X over modulus of x.
I am on the boundary. X.
Okay.
Correct. He was correct. X divided by modulus of x. It points outside, is long 1. But if I evaluate it on the boundary, modulus of x is 1. Okay, so this is just x. So here what do I get? So this is x squared, which on the boundary is 1, and this is sigma n minus 1. The result is sigma n minus 1 divided by n. Okay. So this is another way to show this important relation between these two objects. Okay, so this is called the fundamental solution. Now we will see why we choose this constant, but please keep in mind that this, if you want, is also sigma n minus 1. Okay. Now this is called the fundamental.
Sorry, there is just a typo.
Typo?
Should be x over x, right? So it's 1.
This is
But I am integrating over there,
Ah.
which has norm 1. I agree with you. I should write this, but this is 1. When I am,
Ah,
I agree with you. It's not a mistake. And also, this is correct. Both, they are the same. Okay. Just to simplify. Okay. What I was saying, I think that yes, this is the so-called fundamental solution of the Laplacian. And as you can see, is again singular at the origin. This is crucial. So it is a solution. So this object here is it is singular at the origin. Actually, is undefined for the moment at the origin. So for any x in Rn minus 0, it is called the fundamental solution of the Laplacian. Some authors maybe put a minus here, depends on the choice. Sometimes it may happen that the fundamental solution is minus u, doesn't matter. But there is a remark that one should make here, various remarks. You see, this has a definite sign. With this choice, this is always positive. And is singular, say, at the origin with some power. Also, this is singular at the origin, but it changed sign. is not always positive, can be also negative. So this is a curious difference, interesting and important difference between the two. Okay. Another remark, check what happens in n equal 2, but in n equal larger than 3, what I want to tell you is that u of x is in L1 lock. I mean, it is singular, there is a singularity which is integrable around the origin. So in particular, I mean, for any ball centered at the origin, this integral is finite. Actually, u is positive, it doesn't matter. Well, this is finite. Why is this so? Can you see it? Because if you do the computation in polar coordinates, u is equal to 1, there is a constant, a positive constant, okay, but u is equal to 1 over rho to the n minus 2, and then when we do the computations in polar coordinates, the change of coordinates in terms of rho has a power. Can you remember? Rho to the rho to n is too much. If you do that in 2 dimensions in the plane, which is the Jacobian? Rho. So cannot be rho squared. Rho to the n minus 1. Perfect. The rho, say, then this is this reduces to an integral from 0 to 1, some constant. Okay, in the rho. And this is obviously finite, because actually is even a positive power at the end. Okay. So u is in L1 lock. The gradient of u in n is, so let me compute the gradient of u. So there is some constant here, 1 over n omega n, etc., n minus 2. And then we have a minus, so this is to the 2 minus n. And then we have sorry, x to the n minus 1, right? And then we have x divided by x. And so again, if I do this computation, for the same reason, well, it's a little bit worse, unfortunately, but there is some constant, 1 over rho to the n minus 1, rho to the n minus 1, which again, so 0, 1, 0 r, any balls. And this is finite here. No? But the Hessian is not. Is not L1 here. Because when you do the Hessian, here you gain, I mean, you have 1 over rho to the n, some constant, 1 over rho to the behavior. Each time you differentiate, it becomes worse and worse of 1 unit. Okay. So when you do two derivatives, then you have here 1 over rho to the n, and you multiply by the Jacobian, which is rho to the n minus 1, and then it remains 1 over rho, which is not integrable in the neighborhood of the origin. Okay. So this is an analogy with what we said yesterday, that u second was a measure, but was not representable by a function in L1 log. This is the same. So this is an indication that when I will compute the Laplacian, I will have something much singular as a result. Okay. In any case, this function g of x is perfectly smooth out of the origin. Out of the origin, it is harmonic. So at any point of the origin, if you compute the Laplacian, this is 0. Okay. So now let's see some exercise. Maybe we should do this the analog of the exercise of yesterday, exercise 1. So show that say we do for this is true in any dimension n larger or equal than 2, but let's do the computation in n larger or equal than 3. So minus Laplacian of u equal to delta in the sense of distribution. In which sense we do the Laplacian? Now we do the Laplacian of u in the sense of where u is defined here, fundamental solution. So we made this exercise yesterday in one dimension, and we want to do this today in any dimension, which is much more complicated. Okay, let's see how should we do this. So what does it mean, this? That is, so for any function with compact support, say, if we compute u Laplace of phi, okay, dx, this should be phi. That's 0. This is the meaning. This is the meaning exactly. What does it mean? These are two equivalent ways to say the same thing. Can you understand why which is the idea behind this expression? Because I am integrating by parts twice. I'm integrating by parts twice, and so each time I integrate, I get some boundary term. But now phi is fixed and has compact support. So when I integrate over Rn, there is no boundary term. Okay. So since I integrate twice, the sign here changes twice, and so it remains the same. So the minus here remains minus. Okay, and this is again the duality between delta 0 and phi. Okay. So we have to show this. Once more, u is in L1 lock, right? This integral is actually evaluated only on the support of phi, which is compact. This is bounded on its support. This is integrable on compact sets, so this is well defined. Okay. Now we have to show this equality. Okay. So I use maybe G, doesn't matter. U is G. So how do we show it?
Can we do the same trick of yesterday to integrate once and decompose it into sum of integrals?
No, because that argument is really pretty one-dimensional.
In the compact? Oh, in the compact?
It's really one-dimensional. So what I would do is, first of all, try to avoid the singularity. So fix, so we have phi, say this is the support of phi, I don't know, support of phi. So we fix omega, say, like this. and then we have 0 inside, okay, some 0, I don't know where is 0. So fix a big ball, omega big ball, we have 0 here. And then the idea is to see this as a limit. So to integrate, say, in omega minus b rho. So suppose that 0 is in omega. So this is the ball centered at 0 radius rho. So, and we start to evaluate this u Laplace of phi dx. This way, we kill the singularity of u. Okay? This way we kill the singularity. So what do we do? We apply the divergence theorem. Remember, let me write it. Omega is a big ball. So integral over omega divergence of eta dx equal integral of the boundary, and then we have eta scalar product of the exterior normal. Okay. Fine. So let me use it to the following choice. Eta equal u grad phi in omega. Omega is now omega minus the ball. So we choose omega like omega minus the small ball, which is again a smooth open set, bounded open set. And on this ball we take this. This is a smooth vector field because I have cut out a neighborhood of the singularity. So now eta is perfectly C1, whatever you want. And the divergence of eta is now grad u scalar product grad phi plus u Laplace of phi. So you see here, u Laplace of phi actually appears. Okay, but we can also use another vector field. I exchange phi and u in the same open set, and again everything is very smooth. So the divergence of psi now is grad u grad phi plus phi Laplace of u. Okay. So if I apply the divergence theorem to this choice, what do I get? I get that this. So I integrate this on omega. So this integral must be equal to the integral of a divergence of u grad phi minus the integral of grad u grad phi. And this is what? Now recall again the divergence theorem. We apply now the divergence theorem, which say that this is actually the normal flux on the boundary of omega minus b rho. So the normal flux on the boundary of omega minus b rho is just the normal flux on boundary of b rho So this seems to be minus u the phi over n b rho. Please check the signs because otherwise we... Do you agree with the sign or not?
How did you read this integral?
I am integrating. Oh, yes. So there is also this part. How did I get? I just used Gauss to the Divergence Theorem, but check the sign. Please check the sign. All signs, because otherwise. Remember that we are doing a sort of volume integral in this open set. Okay? So, and we have to use the outward normal to this open set. So, to the boundary of this open set. Here, our test function is 0. So, I mean, we are taking big omega. And so, here, okay, there is a normal outward, but here our test function is 0. So we have only this part of the boundary, but we are considering the outward normal, which is the inward of the ball, so that's why I put the minus in the outward normal. This is outward to the ball, but the minus should be inward to the ball. Okay. I hope that the sign is correct. So this gives us this, and now I exchange u, the role of u, and phi. So exchanging the role of u and phi, I should get a minus integral below phi du du TH-1 minus omega minus below x. This is invariant with respect to the change of u with phi, while this, the others, depends on the choice. Sorry, I'm writing a little bit small because of the blackboard. Can you see it? So what do I get at the end? Now you see, the idea is to take the difference, say, between this and this. Okay. So why I do this? Because there is a term that I don't like and that I want to erase. Is this term here? They appear the same way in the two equalities. So if I take the difference, they disappear. Okay, so we get omega minus d rho u Laplace of phi minus phi Laplace of u dx. This turns out to be, please check the signs. So it turns out to be this zero. So minus u phi 0 plus phi u 0. Okay. Is it okay? Check the signs. I hope they are correct. However, we are out of the rho, and u is harmonic out of the rho. Is a perfectly smooth function. So this is 0. Plus of u is 0. Pointwise, everywhere out of the rho. So out of the rho, this is actually equal to omega minus b rho u Laplace of phi dx. And so minus u Laplace of phi dx. So now, the idea is to pass the limit into this expression. Let rho to 0 plus. This is true for any rho, small enough, say. And then we pass to the limit as rho goes to 0 plus. So what happens to this function? Can I say that this as rho goes to 0 plus?
Is local integrable, so differentiation theorem, maybe a big differentiation.
Yes, perfect. So this is sure. So this is what I want up to a sign.
Sorry, why can't we take the limit again?
It is just the dominated convergence theorem. No, because this is an L1 lock. I mean, you can see that you can pass to the limit.
But in the dominated convergence theorem, all functions were on the same domain, right?
You can multiply by a characteristic function. Okay. Okay. So now we have to pass to the limit into these objects. Okay, let's see what happens to this. To this integral over boundary of 0, u, the phi over the rho, which minus 1. Okay, u goes like I am on the boundary. So u on the boundary here, u is up to a constant, goes like 1 over rho to the n minus 2. I'm doing the proof. I'm doing the proof in this regime now. You can do it by yourself in the case n equal 2, which is extremely important because it's complex analysis, related to complex analysis. So suppose for the moment, so u is going like 1 over rho to the n minus 2. Okay. This is bounded because phi is smooth. So this turns out to be of the order of a constant times 1 over rho to the n minus 2 times the area n minus 1 dimensional area, which goes like a constant rho to the n minus 1. So the result is that the limit is 0. Okay? So this goes to 0, actually. So the hope is that this object, which is what we want up to the sign, the hope is now that this object with the plus should converge to, there is a minus, maybe minus phi of 0. Let's see. Now the sign is always a problem, but so we have to compute now. So let me keep this expression. So we have 1 over n omega n times n minus 2, 1 over x to the n minus 2, and I have to compute the scalar product between the gradient of u and the outward unit normal. Okay. So the gradient of u is equal to this constant n omega n minus 2. I think we already, so there is a 2 minus n here.
We can make minus from
Yes, yes, I have to go very slowly because I am sure that I make a mistake otherwise. So this is 1 over x minus 1 and then x over modulus of x. Am I correct?
Yes.
Huh? And then I have to compute this scalar product. So let me go here. So this can be neglected because it goes to 0. So let's now concentrate on this last term here. So the integral phi b rho, the scalar product mu exterior dHn minus 1. So is what? No? Why? So grad u is some constant. So n minus 2 and 2 minus n cancels, and so there seems to be a minus 1 divided by n omega n. Then we have the scalar product of, and then we have this 1 over rho to the n minus 1.
This is rho n maybe.
Sorry?
It should be n minus 2.
Huh?
It should be n minus 2 because we have n minus 1 and another row.
Another rho.
So we have, well, I mean, this is correct?
Yeah.
Yes, but
Okay, so I put this is 1 over rho to the n minus 1. Then I erase this with this, putting a minus, so 1 minus 1 over n omega n. And then what remains is x over modulus of x, okay, which is rho. Scalar product with x over modulus of x, because this is outward unit normal. So that is 1. X squared divided by x squared is 1. And so this is just rho to the n minus 1.
There is phi also. We got phi.
Yes, sorry, I write phi dHn minus. Thank you. So this is what it is. So this is 1. So we have minus 1 over n omega n, which is sigma n minus 1, by the way. Okay. Rho to the n minus 1. Integral the boundary will be rho. Phi dH minus 1. So this is exactly the mean value up to a sign is exactly the mean value of phi. Which, what does it mean, is the integral divided by the area of the domain of integration. No? Now, it's not impossible, I mean, it's not so difficult to show that since phi is continuous at the center, this limit goes to phi of 0, to phi at the center. Because phi is smooth. Phi is actually continuous at the center. So this goes to minus phi of 0, as rho goes to 0 plus. Fine. Now I hope that, so what we have shown is that passing to the limit in this expression, we get that u Laplace of phi dx over omega is minus phi of 0. Okay? So the result of this computation is this, which is what we want to prove. Okay? So one has to be equal, you see, in n dimension, in n larger or equal than 3. Do by yourself in order to take, I mean, some familiarity with this kind of computation. do the same in n equal to, by home. So home exercise, n equal to. It's a good exercise.
I think the Laplacian should be on your right because we want the Laplacian of u to be the drag delta.
No, the Laplacian of u is a distribution. You cannot write. When you write it such an expression, the idea is exactly to move all derivatives to the smooth test function. So the nice fact about this expression that this does not have any derivative of u. All derivatives are on the function which you can differentiate because it is smooth. This is the basic idea of distributions. U is in L1 log, this is enough to give a meaning to this. Okay? So no problems. This is the basic idea of putting all derivatives where you can do and use integration by parts. Okay? But so which are the ingredients for this proof to go on? I mean, they are the following. Essentially, first of all, there is a singularity, point singularity, and you cannot do computation at that point. But if you remove a small ball, you can do whatever you want. So you change the open set. Instead of omega, you take omega without the ball centered at the singularity. There you can do whatever you want, all integration by parts, whatever. And then you have to pass to the limit as you shrink through the singularity, at the singularity point, right? How can you pass to the limit? Well, you have to remember that the local integrability of the fundamental solution. It is in L1 log, this is enough to pass here the limit. And concerning this term here, concerning this term here, you know the behavior of this on the boundary in terms of rho. But this behavior is eaten by this, because this is rho to the n minus 1 divided by rho to the n minus 2. The presence of this is not important, it's just bounded by a constant. So it is clear that on the boundary this cannot give you really any contribution. The point is here. The idea is that when you make an homotopy here, this goes like rho to the n minus 1. Right? But also this goes exactly like rho to the n minus 1. No? Because u goes like to rho to the 1 divided to rho to the n minus 2. And this, if you differentiate, you become worse. So this gradient goes like 1 over rho to the n minus 1, which is of the same order, opposite of inverse of the same order of this. So they cancel on each other. And the point is to choose that constant. And this I come to maybe your question, in such a way that you get 1 here. Okay, this is just the strategy of the proof. You see, it's not like in one dimension. So we have shown an interesting, famous result. Actually, this is, if you want, the definition of fundamental solution of a linear operator, which is exactly this. Maybe a remark that I should do. In n equal 3 dimensions, the fundamental solution is the Newtonian potential. 1 over norm of x. So it's very important. It is a physical meaning. Okay? In 3 dimensions. Let me see if I should. Maybe I give you an important exercise. two exercises because the proof is exactly the same. So this is a theorem, but I leave you to check at home. Please check it. The same. And now I give you. This is one of the values so-called Green's identities. So this is one Green's identity. I don't know the first, the second Green's identity. I don't know exactly. Okay, so the Green's identity says the following. Suppose that omega is a bounded open set. Open bounded, say, boundary of class C1. Suppose that U and V now are two smooth functions on omega. U and V are two functions, say C2 omega, and we intersect them with some maybe C1 omega bar, just to be sure. Then U Laplace of V. So there is no harmonicity here. Then we can apply this to special cases when one of the two is harmonic. But without harmonicity, we have this. Sorry for the symbols. Don't confuse nu with V and U. Nu is normal, so there is normal. Okay. Okay. The signs are correct. How to show this? Okay, can you see the proof? Proof is at home, but I think that you can do it easily. Why? Because it's if you remember what the proof of the previous result, minus Laplace of G equal delta 0, what do we start with doing some difference between two Gauss-Green formulas, two divergence formulas. So now you take the divergence of U grad V and you expand. So there will be U Laplace of V, okay, and then grad U grad V. And you want to kill grad U grad V, so you expand this with this. So this gives you grad U grad V plus U Laplace V. This gives you grad U grad V plus V Laplace U. Okay? No? Then you integrate and use the Gauss-Green theorem, so this becomes an integral on the boundary. And this is one of the two, you see? And then you take the difference. So it's exactly the same proof. So please do this. It's just it's the beginning of the previous proof. Okay. Fine. This is an exercise. Okay. And then we have as a corollary, say, well, so let us put this as a theorem, but again, is the previous result. So suppose now that suppose that omega is above, U is above. Okay. Then U of x, there is some term and some other signs. Don't want to make mistakes. So I think that this is the gx du omega minus gx du omega. And here we have Laplace of U of y gx y dy.
Is the G the green function?
Or? Yes, sorry. Right. So gx of y is equal now. So let me go back to the notation G for the green, so for the fundamental solution is the translate. I put the singularity at x. Now, so it is 1 over 2 pi log over n equal to 1 over sigma n minus 1 n minus 2 1 over x minus y n minus 2 larger equal than 3 for any y defined. So x is at the singularity and okay, so you have this expression for any x in omega. How should we prove this? I think it's exactly the same proof as before. Can you see it? So how should we prove this? So this is then integrate divergence of u grad v, integrate divergence of v grad u, use divergence theorem, take the difference, okay, of these two expressions. Here instead, so home, here instead what do? Well, we can apply this with u equal u second, so with omega minus v dot x for rho sufficiently small. So I fix x, so I have omega here. Omega is a bounded open set, okay? So I have omega, and then I have x, and then I remove a sufficiently small ball. And then now I am in the situation of a new open set where, which is of class C1, and I can apply the previous theorem to omega minus b rho in place to omega. Okay. And so, and u is u, and v is gx. So I apply the previous theorem on a new open set, removing the singularity. U is this u, but v is now gx. Okay. So what do I get? I get that on the integral omega minus b rho, u Laplace gx minus gx Laplace of u must be equal to this. Okay. And then you should go on with this expression, remembering that Laplace gx is 0. Okay. So it's more or less the same proof. So, as a corollary, so please do this at home. It's the same proof as before, essentially. So, as a corollary, we get that from this corollary, an interesting corollary, that if U is harmonic, then this is identically 0, and therefore U can be written. So this is a representation theorem that represents U at some point of the domain in terms of U itself, or better, the Laplacian of U everywhere, and only the behavior of U and its normal derivative on the boundary of omega. Sort of implicit representation of U through itself. No? So we end up with, if U is harmonic, in particular from this must be 0. So we get that for any x in omega, U of x must be equal to minus the integral of mu omega minus dx mu omega dh and minus 1. Okay, and this will be a starting point, one of the starting point of the next lectures, because you see, remember what we want to do. We want somehow to say something, to solve possibly, who knows, I mean, this kind of problem, Dirichlet condition. This is called Dirichlet condition of the boundary of omega. So if U is harmonic, U must be this for any x in omega. So morally, this is a very good term, right?
You're saying it's G.
Because U is G on the boundary. So here there will be G, and so this part here depends only on the data of the problem. Seems to be a good initial point. The point is that U appears also here, and this is bad. Because this is not the derivative of G. I mean, G is defined on the boundary, and that's it. So I cannot put G here. I can put G here, but I cannot put G here.
Why?
Well, because G is defined just on the boundary, and this is a normal derivative, so it takes into account the values of U inside. No? So, in principle, it could depend on how I extend G inside. So there is, so this term does not depend on the data of the problem. This is given, it's a fundamental solution, is there. G is here, maybe. But here, what do I do? And so the idea will be to modify this term cleverly in order to make it disappear, or maybe transform it. Okay. So this will be one point. Okay. Okay. So now I have to tell you something else. Something else, just a comment. Okay. I want to tell you just one comment, which is important. We know that minus Laplace of, say, G at 0, G, okay, when x is equal to 0, G0 is the previous, the fundamental solution. So this is delta at the origin. Okay. So maybe if you know something about now suppose that you want to solve this. So we have the Poisson equation, not anymore harmonic, but minus Laplace of U given by some f. Like for the electric field. Divergence of E equal 4 pi rho, the density, etc., etc. No? So you have a
Electrodynamics.
in electrostatic.
Electrostatic,
Yes. So that it's important to have also F. No? If you are able to solve this, and you know that this is the solution is this, then you know how to go on. How can you construct the solution, a solution of this knowing the solution of this by convolution of G times the convolution G star F? So this is very vague. To make convolution, we have to make some assumption on f. Okay. But if I am able to solve this, maybe I'm able to write the convolution of G rho star f, because maybe you should know what happens to the Laplace derivative of convolution. You know what happens?
Yes, it sticks to one of them.
To one of them. If one of the two is not smooth, it goes to the other. Okay, so this goes here, but this is delta. And you know what is delta star f?
Yes, that f, that point.
Yes. Yes. So is this. So if you fix any x, you take the delta at x here, and you get what you want. So why this is important is because also not only we found the global radial solution out of the origin, but also because it allows to construct solutions by convolution, taking gx, etc., to other equations where the right-hand side is not zero. There should be some assumption, but so this is one comment which maybe is important. So, well, let us go on with f equals 0, but when there will be f, one expects to have a convolution of the fundamental solution with this object. Okay. This is one comment. Now, okay, now let's start to tell you some remark on the variational relation, variational viewpoint of this similar problem. Okay, so suppose that I introduce this object here. Now, unfortunately, we don't know what are at the moment Sobolev spaces, right? So, which somehow are exactly the correct domain where defining such a kind of energy functional. So let us assume, therefore, that so omega say is bounded and open. In a N. And suppose that, just to fix idea, U is, say, a rather stable class is Lipschitz in omega. Lipschitz means essentially that the gradient of U is in an infinity. As a bound on the, more or less on the derivative, and suppose that omega is also, say, Lipschitz domain. So one could argue, well, if it is Lipschitz, maybe it's not differentiable, so this is not defined. No, it's not the case, because for a Lipschitz function there is a famous theorem that says that at almost every point the Lipschitz function is differentiable in the classical sense. So this object here is almost everywhere defined, and I can integrate. Okay. Okay. Now suppose that you want to minimize. Suppose that you have the following problem: if of f of u, such u is in Lipschitz, and then of course, if I minimize this without any kind of condition, u equals 0 is surely the solution, no? Or u equal constant, so this is 0, doesn't matter. But I need to add some boundary condition. So say G is given, say G is Lipschitz. Okay. Now, suppose that now I have a solution of this. So what I claim is that remark, if, because existence of a solution is not for free,
If it's so harmonic.
Hmm?
If it's so, you should be harmonic function.
So let's try to write a reasonable statement. His idea is, okay, if the minimum exists, should be harmonic.
Should be.
This is what I want to write in this remark. How can I write it without doing stupid nonsense? So first of all, I have to assume that the minimum exists. So if there exists, suppose exists u such that f of u, say let me call this I, okay, u in Lipschitz such that f of u is equal to I. Okay, so u is a minimum. So u is a minimized solution of this. And then, how should I continue? Can I write u is harmonic?
We need to prove Laplacian of u is 0 or something like that.
Yes.
And
No,
maybe
but
we need to do
multiply
some
by
variation
test
of u.
Yes, but my remark was u
It's not smooth
is
enough.
not valid. Yes. So suppose u is also C2. Okay. Then minus Laplace of u equals 0 in omega. You see? Because when I ask u to be a minimizer, I'm just asking that u is a competitor in the class where I am putting the minimum problem. So I'm not asking u in C2. I'm not able to prove that. If I put C2 here, I'm not able to prove that the minimizer exists. Suppose also here, because it's not for free, actually we have to make some assumptions in order to have, but suppose. And suppose also that the minimizer, a minimizer actually, is smooth enough. Then, this is what I want to say, okay?
But if we work, for example, over a Sobolev space and this operator, maybe it is a contraction operator?
It's not,
Maybe lower continuous.
it is not a contraction. It turns out to be a lower semi-continuous and sufficiently coercive to have existence of a minimizer.
Use like sneaker.
If you want, you can also use that. Yes. Okay, so I leave you this, maybe how should you do? You should write home. Do you have idea on how to do this sort of remark? So, you don't have idea, so I give you a hint. So you see this relates harmonic functions with the given Dirichlet condition, say, with minimizers of some sort of energy, intrinsic energy of the problem. So how should we do? So if U is a minimizer, it means that its energy is surely less than or equal than f of U plus lambda phi, okay, for any phi, for any, say, lambda in R, and provided that U plus lambda phi is still inside this class and satisfies the boundary condition. So this means that phi must be Lipschitz itself. And at the boundary, since u is equal to g, phi must be equal to 0. Otherwise, I destroy the boundary condition. Okay? So lip c. There is a small c. Lip with a compact support in omega. So this means that if I look at the function psi of lambda as f of u plus lambda phi, once I fix u and I fix phi, if I look at this function as a function of lambda, this actually turns out to be a C1 function, a one variable, which has a minimum at lambda equals 0, because it is written here. So psi prime, once I show that this is the differentiable at 0, 0 is a minimum point, lambda equals 0 is a minimum point of this function as one variable only, and so I have what it is so-called the Euler-Lagrange equation, which is this. In this case, it's just this. This is the Euler-Lagrange equation.
Sorry, do we prove this or we have it for free?
You have it for free because U is a minimizer, and this is inside the class of competitors.
Yes.
That's
so
enough.
we know already, so if we say that psi have a minimum at 0, just to say it's true.
It's true for every
It's another way to say this.
Okay. I mean, we don't need to prove anything about it.
No, because we want to express the minimality through a differentiable condition, psi prime.
Yeah.
And so we have to show, it's easy to see, it's differential with respect to lambda. And so, inside this, you should be able to prove that essentially, I think that what you get is this condition. For any phi with the as above. You just compute this. So this you have to do, Please do it. So differentiate psi and then put lambda equals 0. Okay, so you first find psi prime of lambda. After that you have found psi prime of lambda, you set lambda equal to 0. And you get this for any test, for any object, for any phi here.
This is gradient or Laplace?
No, it's gradient. It's gradient. And now it comes into play our second assumption. So that now we can integrate by parts and put all derivatives where I can. And since I am supposing u is C2, I can put one derivative here. This becomes a minus Laplacian. See? And what about the boundary condition? No boundary conditions because I have C. So what do I find? I find minus Laplace of u times phi equals 0 for any phi. And there is a lemma in measure theory that says that if under this condition, now Laplace of u is continuous, phi is Lipschitz, if it is true for any phi, then pointwise minus Laplace of phi must be 0. Okay, so this is an interesting remark that makes a connection, relation between classical harmonic functions and minimizer of the so-called Dirichlet integral. Okay, so please do these 3 exercises. I think that you have all tools to do this exercise. Okay, so we see tomorrow there is no lectures. We see the next week on Wednesday at 4, right? Wednesday, Thursday, Friday, 4 o'clock. Okay.